to start here, I want to talk a little bit about your IA intros that I passed back your feedback sheets on. So in general, you know, I saw like 2 or 3 things that I really want to comment on. There's some like direction stuff that like you didn't name stuff the right way or whatever, like that should be relatively clear. The 2 things that I felt like in general we kind of struggled with were, one, like how you described at least when you talk about the tests you were doing. I want to take a moment and read an intro from another student that I thought did a pretty good job when they talked about the tests, so you guys can hear what I'm looking for. So this is all I want you to do. Like, there's stuff that's wrong with this paper also, so don't like, it's not like the perfect thing, but I thought they did a good job when they talked about the tests. So that's the part that I want you to listen for. So I'll take a minute and read that, and then we can unpack that a little bit. If you guys feel like, oh, I see what you're saying, then we'll move on and talk about the next thing and the next, you know. So I have some examples here to read for you guys. Growing up, my life revolved around 3 sports: football, basketball, and baseball. As I am now in the home stretch of youth and high school sports, I have given up both basketball and baseball. However, baseball is still the sport I have remained particularly interested in all my life. While watching baseball games, I always wondered whether the speed of the pitcher's pitch is more likely to be the reason for the batter to strike out over things such as the curve or tendencies of the pitcher. This love of the game and want for knowledge of the game has incentivized me to discover how much the speed of a pitch is dependent on a batter striking out or not. In doing this, I plan to prove the higher the speed of the pitch, the better chance the pitcher has at striking out the batter. In this experiment, my independent variable will be the number of strikeouts by a pitcher, and the dependent variable will be the pitcher's average pitch speed. The higher the speed of the pitch, the better the chance the pitcher has at striking out the batter, no matter the type of pitch that is being thrown or the pitcher throwing the pitch. My data collection consists of a list of 100 random MLB pitchers and their average pitch speed, and the number of strikeouts they had last season, as well as their total number of pitches thrown last year as a whole. With these data sets, I plan to perform a scatter plot test, a correlation test, and a chi-square test. A scatter plot test is going to be used to help me identify the correlation between the 2 variables and their strength, type of relationship, and any possible outliers. With the scatter plot, I hope to show that as the speed of the pitches increases, the dots on the chart get more bunched up. The correlation test is going to be used to give me a better idea of the true strength of the 2 variables, and I hope this shows there's a strong correlation between pitch speed and strikeouts. Finally, the chi-squared test is going to be used to see if the number of strikeouts is dependent or independent of the average pitch speed. I hope this test shows that the number of strikeouts is dependent on the average pitch speed. Overall, these tests are going to help me figure out the relationships between the 2 variables. So what I thought this author did a nice job of is when they introduced each one of these 3 statistics that they're going to be doing in their paper, they talked about what it was going to show. Could they have done more depth there? Yes, but that was, I thought, an acceptable level of depth in terms of what the statistic could show you. And then afterwards, they talked about what they would hope to see from their data, right? So everybody kind of, you see what I'm saying there? And as far as like organization of paper, that goes a long way for the reader going, okay, I know what to expect here. We're going to talk about this thing, and this thing. This is what they're hoping, you know, that would reinforce what they believe to be true. I thought that the author does a decent job of doing that, okay? The other part that, or another part that I thought that in general, not very many of us did a very good job of, was the personal engagement piece. So I have another paper by a different student or another intro by a different student that I thought did a really nice job of the personal engagement. Then I want to read you this one, and that's what I want you to listen for here, is that the idea of why this thing that this topic that they've chosen, why this is important, and who it might be important to, okay? As a student, I've often heard about the importance of balancing academics, activities, and social life, but sleep usually doesn't get the same attention. I've noticed personally that lack of sleep affects my mood, focus, and stress levels. When I don't sleep well, I often feel overwhelmed and unable to handle stress effectively. This led me to the question, how strongly are sleep and stress linked? And could more sleep really help reduce stress? For my internal assessment, I wanted to research a topic that is both scientifically relevant and personally meaningful. Understanding how sleep affects stress might not only improve my daily life, but also offer helpful information for others. With the high demands of students who often sacrifice sleep to meet commitments, if there's a clear link between more sleep and lower stress, it could encourage students to prioritize sleep as a tool for managing stress and overall health. My independent variable is the number of hours of sleep per night, and my dependent variable is stress level. This project aims to explore whether the hours of sleep a student gets each night affect their stress levels. I'm investigating if more sleep is linked to lower stress among students. Based on experience and research, I expect a negative correlation between sleep and stress, meaning as sleep hours increase, stress levels should decrease. This assumption matches with studies that suggest sleep is crucial for emotional regulation and mental health. By focusing on high school students, I hope the results will be relevant to people in similar situations who face academic and social pressures, often at the expense of sleep. If there's a clear connection, the finding could provide advice for managing stress through sleep. To test my hypothesis, I'll survey a sample of students. I plan to get responses from at least 30 participants to make the data significant. While the sample may not be fully random, it should represent the student population well enough for this study. For my scatter plot, the first step is to create a scatter plot to visualize any relationship between sleep and stress levels. The scatter plot should help identify any trends. If my hypothesis is correct, I should see a downward trend, showing that as sleep increases, stress decreases. I'll calculate Pearson's correlation coefficient to measure the strength and direction of the relationship. The coefficient ranges from -1 to 1. A negative correlation coefficient close to -1 would support my hypothesis that more sleep correlates with lower stress. Even if the correlation isn't particularly strong, any negative value might show a trend worth looking at, especially if it encourages students to prioritize sleep. By combining insights from the scatter plot with Pearson's correlation analysis, I aim to conclude on the relationship between sleep and stress among students. If my hypothesis holds true, this result could remind students of the importance of sleep in managing mental health. It could also encourage schools and educators to promote healthy sleep habits as part of stress management strategies. Through this study, I hope to gain insights that are both personal and broadly relevant. Approaching this project from both a personal and scientific perspective, I hope the findings will be meaningful and applicable to everyday life. What this student did, I thought, quite effectively was, one, gave a personal motivation for why they chose this, but even better, they talked about why this topic would be important, why the answer to this question would be meaningful. They clearly stated who it would be meaningful to, either other students or even, professionals like teachers or counselors or something of that ilk, and as to why it would be important, like how they could use the result of this study to help other people. I thought they did a really nice job of hitting on that. And was this a little grandiose? Like, does the high school kids project? Sure, but that's okay. Like, go a little bit over the top with like the personal engagement side and like theoretically what, if I found the answer to this, who would that help? How could that help them? And really kind of like reach a little bit with it. It's okay. That's what we're looking to do here, is that you understand that what you're doing, or that mathematics in general, isn't done for the sake of doing it. It's done with a purpose in mind, whether it's to help people or make money or whatever, that there's a reason behind doing this. So if you are doing a project that relates to students, talk about, like students or the educational system, or like teachers or parents or counselors, or like group in those, wrap in those other groups and how they could use the result of your study to help. If your thing is about sports, like who else would benefit from this? Would agents or players or coaches or talent identification? Would team management build a team differently based on the results of this? Would they prioritizing drafting or developing certain types of players? Sports is it's a business at the end. Like, could they use your result to potentially make more money by gaining an edge in their competition? If you're talking about movies, like who else would be interested in the results of this? Would studio executives, actors, directors, movie theater owners, like movie financiers, producers, like advertisers, like who else would be interested in the result here in a way to like make some money off of this? You guys kind of see what I'm saying here? And a lot of us kind of did an okay job of connecting it to ourselves and maybe danced around like the idea of like who could be else benefit from it was like kind of there, but you don't say it. Like come right out and say it. And be like, a little over the top with like how important this could be. Like this student here that wrote what I just read did a really nice job of like, maybe it's a little bit of a stretch, but it's not that far of a stretch of how important the result of this could be and how it could be used and by who, right? You kind of get what I'm saying? So the one other thing that I would mention here that again, I think is worth mentioning that again, not a lot of us did or we didn't do a very good job of is probably somewhere in your introduction, you should clearly state the population that you're studying. So in that first paper I read about the Major League Baseball pitchers, that student would have wanted to say the population is all baseball players, because you have to make sure that you're going to, have a valid chi-squared test at the end, so your sample can't be too big, right? If you talk about all baseball players, certainly 100 pitchers is not more than 10% of the population. The second student would have wanted to say the population was all high school seniors, because certainly the 100 or so kids that they would get to answer their survey are not going to represent 10% of those students. And then further on, when you do your data sections, you can talk about, well, when I did my sampling, I can't sample all baseball players because we're not recording pitch speeds and strikeouts for like youth baseball and high school baseball probably, and collegiate baseball, maybe you're probably even not. Like, and if they do, it's probably not publicly available, or I couldn't find it publicly available. So I had to limit my sample to a publicly available data set that was Major League Baseball pitchers. Now, that student, when I talked to them, we talked about like from their sample space that they're going to consider pitchers that have thrown at least some number of pitches, and they'd want to talk about that there, that I limited my sample space of Major League pitchers with ones that had thrown like at least 1,000 pitches or something in the season, so that I had like guys that actually, could rack up some strikeouts because they had a chance to actually throw some pitches. If you're talking about sampling students, you'd be like, well, realistically, I'm a high school student in Michigan. I can't collect data randomly from high school students worldwide. I limited my sample because of convenience to students at my high school, and so that's something you would discuss in your data section. But I think in your introduction, you would at least want to clearly specify the population that you're targeting. Does that you guys feel a little bit better about like what to do differently, or hearing what I thought like students did a good job of this or that? You can kind of see the difference between what you wrote and what we read here. Now, in general, almost no one did really well on this. I will, if you want to take a second shot at this and resubmit, I'll look at it again, okay? You may do that, and I'll assign you a different grade for it if you want to. You don't have to. If you haven't turned one in yet, you're not going to get a second chance. When you turn it in, it'll be the only time you get it because you're getting this additional feedback that nobody else got on their first chance. So this will count as your second if you haven't turned one in yet. And let's try to have those by Thursday next week. Okay? So you don't need to write a fresh new one. You can take your existing introduction that you've already written and make additions or deletions, or like elaborate on places where I was I didn't do enough here or there, or I did enough there, so I'm going to leave that part alone, but I'll add something else here, and maybe I did too much, I'll take something out there. But you can use the same file, that's fine. Like, change it up, whatever you need to. Or start fresh if you're like, what I did was just hot garbage, I'm just going to start fresh, and I think I'll do better than trying to edit something that I wasn't particularly happy with. You know, whatever you want to do is fine. Do we feel a bit better about what I'm looking for? Again, I try not to do this in the beginning because I want to give you a chance to like do what you think and it give you an idea, like a reality check as to like how good was this? So you get it when it's time to sit down and write the thing for real. That's like, oh, I really need to proofread this. I really need to like think about like what these sections need to contain. I need to go back and make sure I'm looking at the criterias in the OneNote for the IA about what should be in there, what shouldn't be in there, so that I'm hitting all the benchmarks and that I'm really elaborating enough on the things that need to be elaborated on. Again, like an introduction, your introduction should probably be like a page and a half. If you're over that, that's fine. There's not like a hard word count to this. And some of us are really efficient writers and some of us aren't. Some of us, can say in a page what someone else takes a page, 2 pages to do, just because of, our skill as a writer. So don't worry about the words. Like, it's done when it's done. But I'd say on average, your introduction should probably be closer to that page and a half than to a page to really kind of get everything in there that you need. You guys feel better? Okay. So the other thing I want to remind you is that the Chapter 14 test is scheduled for Tuesday next week. Make sure that you guys look at the test description on OneNote. It'll basically be the quiz plus the linear regression pieces, which I don't think are difficult, right? You're just basically using the formula or using your calculator to get the equation to pop out. Or if I give you the statistics, you should be able to plug them into the formula to get the equation. And once you get the equation, if I ask you to make a prediction, you should be able to do that using the equation. What's the one trick I'm going to play on you, though, about making a prediction?
You can't do it.
Yes, if it's extrapolation, you should not use the model to make a prediction, right? So you definitely need to check for that first before plugging anything in. Okay? Extrapolation. You need to definitely check to make sure you're not doing extrapolation before you plug anything into a model.
Okay.
Mm-hmm. All right. How do you guys, you're okay on the Chapter 14? The quizzes were pretty good, by and large. You might want to run through another Spearman example or two. So that was a little shaky for some of us, but overall, things went pretty good. I would mention that changing units does not affect correlation. That was a question that I think the most missed part of the quiz was that question at the end. If you think about it, if you have things in a perfect straight line, if I multiply all the x coordinates of the things in the line by 3, like the line will stretch out, but it'll still be in a straight line, right? So correlation is not going to be affected by a unit change. You get what I'm saying? That's the way to think about it. Remember, again, that the Pearson correlation is just describing like how linear something is. So a unit change will not affect that. Or if you switch which variable is independent, dependent, right? If it's xy's and I switch them to be yx's, is it still going to make a straight line? Yeah, of course, it's still going to make a straight line. So like that doesn't matter. You know, like, again, that's another common question. Everybody feel okay about the test? I'm going to do a couple slides from chapter 8 here to start. We'll probably have, I'm going to go through slide 8 and then just give you some time to like, seems like everybody needs a break this week. So rather than like hammering through the entire period, we'll just stop after like 8 slides or so and just call it good. Reminder for Sunday's problem set, it's going to be section 14.3. Test on Tuesday, and then IA intro redo, if you choose to do it, it's optional, is Thursday. Okay? No. All right. So in chapter 8, we're going to be talking about probability. Now, we've talked a little bit about probability already so far this year, right? When we did the t-test and the chi-squared test, one of the outputs we got was a p-value. That p stood for probability. So we've done a little bit with probability so far, but we're going to really kind of develop the whole picture here for probability here in this chapter and look at how we calculate probabilities. Now, we won't be calculating probability like we did for a t-test or chi-squared test because that's a pretty complicated calculation to do by hand. But we will do some probability calculation by hand in some more class-appropriate contexts. But like calculating that area under the curve that the calculator is doing for us in the chi-square test or t-test is beyond the scope of what I would ask you to do in this class. In fact, that's like a graduate level statistics course question. So don't worry, that's not coming. All right. So when we talk about probability, what are we really talking about here? So when we talk about like probability, we're talking about the idea that chance behavior, although unpredictable in the short run, eventually has like a regular and decidable pattern in the long run. And this is kind of illustrated by what we call the law of large numbers. So like if I flip a coin 10 times and I get 8 heads, do you think the heads are going to come up 80% of the time? If I flip the coin like 1,000 times, what are you going to expect? Much closer to 50-50, right? Because although over the short run, you might get some aberrant behavior, eventually that probability is just going to kind of regress to the mean and settle down towards what we'd expect, assuming the coin is fair, right? So when I say a fair coin, that means that like the odds of getting heads and tails are identical, that's evenly weighted. If you are a cheater, you might try to design a coin that is unfair, that comes up one side more than the other. If you wanted to test that, you could do an experiment and flip the coin like 1,000 times and look at the ratio and be like, ooh, I think this unfair coin I've made is like 65% heads and 35% tails, because over 1,000 trials, I got 651 heads and 349 tails or something. Does everybody feel okay with this idea? So the law of large numbers, especially experimentally, can help us try to determine like the probability of something happening. If it's a situation where it's like, I don't know what what are the odds like what's the probability it rains just on a given day, any given day, not like look at the number of days it rains and how likely it is to rain on December 11th for the past century, and maybe use that. So here's like a visual example. So this is just a flipping a coin situation. So the first round I flipped the coin like 20 times, and you know, like seems like the odds of getting heads is slightly less than 50%. Well, what if I do it for 500 times, even though I get some aberrant behavior in the beginning? Finally start settling down to basically right around 50%, right? And the more flips I get, the more I would expect, if it's a fair coin, to land right around like, you know, 50.1 to 49.9 or something, you know, like where it's basically the same thing. If I could flip the coin infinitely many times, I'd expect it to be dead 50-50. Feel okay? Okay. So we say that probability of an outcome of a chance process is a number between 0 and 1 that describes the proportion of times the outcome would occur in a very long series of repetitions. The thing that I will be picky about, and I will tell you right now on the next test or whatever, is if you give me a probability that is not between 0 and 1, I'm giving you no points for that problem. You've given me an insane answer. If you give me a negative probability or a probability greater than 100%, right, a number past 1, you'll get no points. I'll say the same thing about the R's for this next test. If you give me an R value that's less than -1 or greater than +1, I'll give you no points because it's an insane answer. Everybody's okay? Okay. All right, so some misconceptions about probability. So the first is called the myth of the short run regularity. So the idea that probability is, the idea of probability is that randomness is predictable in the long run. Our intuition tells us that that random phenomenon should also be predictable in the short run. However, that probability does not hold, right? If I talk about the coin flipping example, I'm flipping the coin 10 times. Not every time I do that am I going to get 5 heads and 5 tails, right? Some of the times I'll flip and get 10 heads and no tails. Not very likely. Might have to do a lot of trials, but that's an outcome that can happen. Doesn't mean there's anything wrong with my coin. Just was a weird, you know, just was a weird sample. The other is the law of averages. So if you've gone, I know nobody's old enough to go to a casino, but you've probably seen like on TV or whatever at the casinos, they'll have, for like the roulette table, they have a board that'll tell you like what number the ball is landed on for like the last 10 or 20 previous spins. And what you'll see is if it's been like, you know, red, landed on a red number like 10 times in a row, people flock to bet on the green, or the black, I should say, thinking that, oh, it's black is due, right? Because we've gotten 10 reds in a row. No, sir. The probability of landing on black has not changed based on this past events. All these events are independent. What's happened before has not changed the probability. Nothing is due. These are all independent events. The casinos put that board there to trick you into doing dumb things like believing that, oh, my number's due to come up. No, nothing is due, right? Like the odds of you getting your number, color, or whatever coming up is not changed just because you've gotten a weird streak of something else happened. Does everybody feel okay there? Okay. So what we're going to be doing here to start in Chapter 8 is building out what's called a probability model, like the structure, the mathematical structure that we're going to use to kind of calculate probabilities. So in doing that, we're going to throw a bunch of vocab at you and a bunch of notation, okay? And the vocab can be hard because sometimes it's overlapping, okay? In particular, we'll talk about outcomes and events. And sometimes an event is an outcome, and sometimes an outcome is a bunch of events. So the vocabulary can be a little bit difficult, but that's why I want to go through and make sure we're doing a careful job on this. Okay. So we want to start by defining what we mean by an outcome. An outcome is just the result of some kind of a trial. So, for example, if we talk about flipping a coin, that would be our trial. What are the outcomes of flipping a coin? Heads or tails, right? If it's rolling a die, like a normal board game Monopoly die, it's the numbers 1, 2, 3, 4, 5, 6, right? If it's drawing a card out of a standard deck of cards, it's, whatever the different suits of the cards are, right? Like Ace of Diamonds is one outcome. Everybody's okay with that? If we look at all possible outcomes, we take those together and group it together. That set of all possible outcomes we call the sample space. So this is an example of a place where students will get confused. Let's say we talk about flipping 2 coins at the same time. The different outcomes of that would be like 2 heads, head tail, tail head, or 2 tails. Everybody's okay with that? Sure. Okay. If we talk about an event being, getting 1 head and 1 tail, there's 2 ways that could happen, right? There's 2 different outcomes that have 1 head and 1 tail. So in particular, events and outcomes, we have to be careful about our vocabulary there. We'll define event in just a minute. I'm just talking about it now. And then the last vocab for this slide is a probability model. So a probability model consists of 2 things. It has a sample space, so all the possible outcomes, and second, a probability attached to each of those outcomes. So if our trial is flipping a single coin, what is the sample space? Heads, tails. 2 things in our sample space, right? The probability attached to each of them is 50%, right? If we're rolling 1 die, there are 6 outcomes, 1, 2, 3, 4, 5, and 6, each with a probability of 1 in 6. If I flip 2 coins, the sample space has 4 outcomes, heads, 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 tails, tails, heads, tails, tails, each of those with 1/4. If I roll 2 die at the same time, I have 36 outcomes, 1 and 1, 2 and 1, 1 and 2, and you go through and you enumerate all of those. I'm not going to do that now because, yikes, that's a lot of talking. Each of them has a 1 in 36 chance. You guys kind of get the feeling here? Okay. All right. So let's go back to this idea of rolling 2 die. So this is the sample space, right? Notice I've colored 1 die one color and 1 die the other color, so it's easy to see that 2, 1 is different than 1, 2. Is everybody okay with that? So I have 36 total outcomes here. And if it's fair, if the dice are fair, each of them is equally likely. So it's a 1 out of 36 chance for each of them. Everybody's okay with this idea? Now, if you're playing a board game and you're trying to land on like Boardwalk while you're playing Monopoly and it's 7 spaces away, you don't care if you roll a 2 and a 5 or a 1 and a 6 or a 6 and a 1. None of that matters to you, right? You just want to roll a roll that totals to 7, right? So that's this type of situation of what we're going to do is define an event. So an event is a collection of outcomes from some process. So like rolling a 7 total is an example of an event. That event contains 1, 2, 3, 4, 5, 6 outcomes. Everybody's okay? Now, if the event was rolling snake eyes, that event contains 1 outcome. So rolling snake eyes or 2 1s is an event, and it's also an outcome. This is where it gets confusing, right? Because if the event has just 1 outcome in it, then the outcome and the event are the same thing. But in general, that's not the case. Everybody's okay? Again, since this event is a set, it's a set of outcomes. Typically, we designate it with a capital letter like A, B, C, etc. And if I want the probability of that event, I write P of A. So if A is my event, if I want to calculate the probability of that, if I want the number, I write P of A. So let's go back to our dice rolling. And if our event is that the sum of the 2 dice is 5, let's calculate the probability for that. So let's see. I see 1, 2, 3, 4 ways of rolling 5. And if they're each 1 in 36, the probability of rolling a 5 then would be 4 out of 36. Is everybody okay there? 136 plus 136 plus 136 plus 136. So 436. What if I wanted to know what's the probability of not rolling a 5? Say like you're 5 spaces away on the Monopoly board from Boardwalk, but your opponent has got a hotel on there and you're like, I do not want to land on that anywhere but there. What's the probability of not rolling a 5? 32 out of 36. How'd you do that so quickly?
You just do 4 minus 36. It's like all the rest of the outcomes.
Yeah, so you did like 1 minus rolling a 5. Could you have also gone back and went, okay, 1, not 5, 2, not 5, 3, not 5, oh, 5, 4, not a 5, 6, and counted it that way?
I know that.
Yeah, you could have. But what's the disadvantage of doing it that way?
It takes forever.
Yeah, it takes forever, right? So this idea of doing everything minus what you don't want, this is all like probability spaces have this property. It's a very nice shortcut to use. In particular, it has a name. So when we say our event is not something, so that's called a complement. So like the probability of not A, that's what B is, right? If A is rolling a 5 and B is not a 5, B is not A. The formula to calculate probability of not A would be 1 minus the probability of A. That's an effective shortcut almost always. Everybody's okay? Now, with probabilities, the sample space is a set of numbers. An event is a set of outcomes. I should say the sample space is a set of outcomes, of all outcomes. An event is a set of outcomes. We're talking a lot about sets. Probably been a long time since like Algebra 2, since you've talked about sets in any kind of detail. let's go back and refresh our memory about some of the set notation. So when I'm describing a set, typically I'm going to use the curly brackets, and then I'll list the things contained in that set, right? If I don't have the curly brackets, is it a set? That's like the middle school lunch ending or something, I don't know. If I don't have the curly brackets, is it a set? No. If I ask you for a set of things and you don't write the curly brackets and you just write a list, am I going to mark down on it? Yes. Okay. Another reminder about sets. Sets do not contain repeated elements. So if you list the same thing in the set twice, am I going to mark you down for this? Yes. Okay, no repeats in a set. If you write a list, can you have repeats? Yes. A set, though, cannot. All right. If I write n of some set, that n is asking us to calculate the number of things in the set. So if my set is the numbers 1, 2, 3, and 4, n of that set is 4, because there's 4 things in the set. 1, 2, 3, and 4. Is everybody okay there? If I use the capital letter U, that stands for the universal set. That's the entire population being considered. For us, when dealing with probabilities, it's the same as the sample space, right? Or probably. I guess technically, like, you know, if you're talking about rolling 2 die, probability of getting a 0 or getting a 42, well, those are all probability zeros, right? Like if I roll 2 6-sided die, I can't get 0, I can't get 42. You know, I'm stuck between 1 and 12. Another special set is the empty set. That's a set containing nothing. So curly bracket, and then the other curly bracket is a set, even though there's nothing in it. It's the empty set. We give it a special symbol. That 0 with a slash through it is the empty set. Everybody's okay there? This little symbol here that looks like an E, like a little like curvy capital E, stands for element. So that's describing the things inside of the set. So for example, if my set is the numbers 1, 2, 3, and 4, I could write 1, E, like this symbol, set 1, 2, 3, 4, because 1 is a member of that set 1, 2, 3, 4. You guys get what I'm saying here? Likewise, if I put a little slash through that symbol, that means it's not a member of the set. So if I use that same set 1, 2, 3, 4, I could write 5, and then this symbol is not a member of the set 1, 2, 3, 4, because 5 isn't one of the numbers 1, 2, 3, or 4. Is everybody okay with that idea? This symbol here is called a cap. It stands for intersection. This is a set operation. I can only do the intersection of one set with another set. I can't do the intersection of an element and a set. So if I have the set 1, 2, 3, 4, and I have the set 1, 3, 5, 7, the intersection between the two sets is going to be the set 1, 3. Just the things that are in common to both, right? You can think about it as the word and. What is in set A and in set B? The other symbol here is called a cup. That stands for the union of the two sets. So if I have the set 1, 2, 3, 4 and the set 1, 3, 5, 7, if I'm looking at the union of those two, it is the set 1, 2, 3, 4, 5, 7. It is anything in the first set and anything in the second set, but no repeats. I'm not writing 1 twice. I'm not writing 3 twice, even though they occur in 2 places. Is everybody okay with that? You can think about the union as the word or. If you tell your mother, I'd like hamburgers, or I'd like pizza, if she brings you back hamburgers, are you happy? Yes. If she brings you back pizza, are you happy? If she brings you back both, are you happy?
Yeah.
Okay. It's a good day. All right. The last symbol is this subset symbol. So it's kind of like looks like a little bit of a stretched out letter C. So a subset symbol also occurs between 2 sets. The most common mistake is students confuse the element of and subset of symbol. So if I have the set 1, 2, 3, 4, 1 is an element of that set. The set 1, where I put the curly braces around it, is a subset of 1, 2, 3, 4. Right? So if there's curlies around it, you can be a subset. If there's no curlies on it, it's an element. Everybody's okay with that? Now, we have 2 different subset symbols. This is not tremendously important, but I'll explain to you what the difference is between them. The first one is a proper subset, which means that it has to be not the full set. So like if it has the line under it, it could also be the full set. So like the set 1, 2, 3, 4 is this kind of a subset with 1, 2, 3, the set 1, 2, 3, 4, but not this one. You can think about it like the less than versus less than or equal to, right? Like 1 is less than or equal to 5, or X means that 1 could be in there, right? Equality is okay. If it's 1 is less than X, well then 1 isn't in there. Equality is not okay. You guys get what I mean there? Okay. I think I got one more slide and we'll be done. One way, since we're going to be talking about sets here, that these are linked to probabilities we've seen, because we're defining most of the probabilities as in terms of these sets, we're going to be using Venn diagrams. A Venn diagram is just a really nice visual way to represent a set. So a Venn diagram has a rectangle or a square to represent the universal set. And then our sets inside of that universal set will be circles. So, for example, if I have this set of outcomes A, that's the white circle. The green area is the set of all the things that are not A. The stuff that is not A has a special name. It's called the complement of A. And the symbol we use to represent that is that little like apostrophe on the A. So if you say A prime or the complement of A or not A, those are all like interchangeable. And there's a bunch of notations to denote a complement. I think our textbook uses primes exclusively. But if you're Googling, you might see the complement represented with like a bar on the top. You could see it with like a squiggle in front of it, or like the negation in front of it, or like a C in the exponent. There's lots of different notations. So one special piece of vocabulary we have that will often be of interest to us between 2 sets is if they're mutually exclusive. Or we might use the word disjoint. Sets that are mutually exclusive share no elements in common. So for example, the set 1, 2, 3, 4 and the set 6, 7, 8, 9, 10 are mutually exclusive. There's nothing in common between them. If I wanted to take the intersection of the set 1, 2, 3, 4 with the set 6, 7, 8, 9, 10, what is the intersection of those 2 sets? It is the empty set, right? There's nothing in common between them. There's no element that's in 1, 2, 3, 4 that's also in set 6, 7, 8, 9, 10. The intersection is not 0. It's still a set, but but it's the empty set. It's the set of nothing. Everybody's okay? If I looked at the union of the set 1, 2, 3, 4 and the set 6, 7, 8, 9, 10, the union of those is 1, 2, 3, 4, 6, 7, 8, 9, 10. It's everything in each of them. No repeats though. If my universal set is the numbers 1 through 10, what is going to be the complement of the union? Yeah, so it's the 1 through 4 and then 6 through 10. We union those together. What's the complement of that? It's 5.
Oh, no.
It's the only thing in the universal set that's not in there. If I'd written this stuff down, you would have gotten it. You're doing fine. You're doing fine. It's the end of the day. Okay? What's the complement of the intersection?
It's the opposite of whatever the complement is.
So the intersection of 1, 2, 3, 4 and 6, 7, 8, 9, 10 was the empty set. What's the complement?
Not that set.
Which means
All the not.
the universal, right? Means everything. It'd be the numbers 1 through 10 in this example. Does that feel okay? Okay. And we're going to stop here. This is enough for today. Okay?